So pause on taking notes. I know that we just saw the product rule today, but hopefully you've seen it in lecture already. So just as a quick recap, if I have f times g times h, and I take the derivative, I had three things, so I write it 3 times. I have addition between them, and I chase down the derivative. Somebody pick a number between 5 and 10. 7, awesome. 7, I'm gonna fit 7 in, I promise. Okay, so I'm gonna have 1, 2, 3, 4, 5, 6, 7. I'm being lazy. That's a bunch of F's multiplied together. How many of them? 7. I don't know why I showed you a 4. 7. Okay, so when I take the derivative, I'm gonna write those 7 F's 7 times. Okay, 1, 2, 3, 4, 5, 6, 7. I use F's because I can be lazy. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. How to do 1, 2, 3, 4, 5, 6. Okay, good thing no one chose a number bigger than 7. It would not have fit 1, 2, 3, 4, 5, 6, 7. Awesome. Okay, we were doing a bunch of product rules. Well, what goes with multiplication? Addition. And then I'm going to chase down the derivative. Sweet, it even worked out with the number of syllables for the win. Okay, so let's say that I had that and then I wanted to kind of simplify it. So I'm looking at each of these 7 pieces and saying, well, what do they have in common? Each of them has an F prime. And each of them has 1, 2, 3, 4, 5, 6 F's that are not primed. Well, those 6 F's that are not primed, the shortcut way of writing F times F times F times F times F times F is F to the 6th. And then I've got that 1 F that was primed. But the same thing happens here. I've got 6 of those F's and then an F prime, and 6 of those F's and an F prime, 6 of the F's and the 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 F prime. So in total, I've got 1, 2, 3, 4, 5, 6, 7 sets of 6 not primed F's and 1 primed F. And this whole thing started because I had 7 of these F's multiplied together, which we know the shortcut way of writing that is F to the 7th. And my guess is that your keen powers of observation might lead you to say, oh, hey, there's a way shorter way to get from here to here without writing all that garbage out. So that if I had something that looked like F to the 100 and I took the derivative, I'm not gonna write out 100 of those F's. I'm gonna say, oh, I know there's gonna be 100 sets. And each of those 100 sets is gonna have 99 of the F's that are not primed and 1 F that is. Yeah.
Is this a lot like the
It is. And so the chain rule comes directly from the product rule, at least in terms of looking at things with exponents. Now we kind of have to extrapolate that to the chain rule for other things, but here's the part where you can start taking notes again. So if I've got some kind of function, like, let's say I had, 5x squared plus 3x raised to the 80th power, and I wanted to take the derivative, I'm not going to write out 80 of those product rule things. That general power rule says, oh, well, I just take the exponent and pull it down in front, subtract 1 from the exponent, and then remember that I'm going to have to multiply by the derivative of what's on the inside. And so this time, what's on the inside there, I've got 5x squared plus 3x, which will be 10x plus 3. This is really the thing that we're going to use the most. So I want to make sure that we get more practice with this idea. Yeah. So this is just another notation that says take the derivative. Yep. Yep. This is often the notation that we use if like we're not writing it out in function notation. I'm just saying, here's the thing I'm taking the derivative of. Yeah. Yeah, so the question about where the 10x plus 3 came from. So this part is the derivative of what was in parentheses. Let's do a bunch more examples of this. I'm going to go ahead and flip it and we'll get more practice. So if my starting function looked like 2x to the 4th minus 9x squared, and that whole thing was raised to the 5th power, again, you could go multiply all that garbage out, but we're not going to take the time to do that. We are instead going to use the chain rule. And chain because it's like a chain of stuff, right? So in general with the chain rule, I'm looking at this and saying, hey, I've got some stuff, there's stuff in there, and it's raised to the 5th power. So if I want to take that derivative, I'm going to end up with 5 times the stuff to the 4th power times the derivative of the inside. So this piece out here is going to be the derivative of the inside. So I'll just leave that. I don't know where the 3 came from. I was like looking at a 2 and a 4 and my brain wrote a 3. 2x to the 4th minus 9x squared. That part we're leaving alone. And then we're going to multiply by the derivative of that. So that derivative, I'll have bring the power down. So 2 times 4 is 8. Subtract 1 from the exponent. Then over here, I'll bring the power down. So 2 times 9 is 18. Subtracting 1 from the exponent just leaves me with an x. Let's talk about a couple of examples of problems that look straightforward, but people make a lot of mistakes on. So here are a couple. The first one is something like, I said, my function is tangent cubed x, and I was asking you to take the derivative. It's possible that you would do this perfectly correctly, but what I find is that if we take a minute to rewrite this in slightly different notation, people are less likely to make a mistake. So I've got tangent with a 3 up there and an x, which means we have tangent of x, the whole thing is cubed. So when I go to take that derivative, I'm going to use the chain rule. I've got some stuff that's cubed. So I'm going to end up with 3 times that stuff squared times the derivative of what's inside, the derivative of that stuff. So the derivative of tangent of x, I know we've just learned it today, but that's going to be secant squared x. I'm going to move the 3. And now we have a completely different problem. Visually, it's not that different. But this means that I have tangent as sort of an outside function with an inside function of x cubed. So when I go to take this derivative, I look at that outside function, which is tangent, and I take its derivative. So the derivative of tangent of something is secant squared of something. And then the chain rule says I multiply by the derivative of what was on the inside. And the derivative of x cubed is 3x squared. I'm going to do one more in this family. And if my question was that I had tangent of 3x and I needed to take the derivative, this one says that I have tangent of 3x. Tangent, again, is like my outside function. So when I take the derivative of tangent, I'll end up with secant squared of the stuff times the derivative of the inside. And the derivative of 3x is 3. So 3 functions that all started out looking pretty similar, but their derivatives are really different because those 3 functions, although visually they were similar, they were very different functions. Should we do some more that are common places where people make mistakes? So another deceptively simple looking thing. If my function was something like e to the 5x, the derivative of e to the something is e to the something. But this chain rule piece says we've got to remember to multiply by the derivative of whatever the something was. So when I take the derivative here, I would get e to the 5x. We're just going to write it all over again, but times 5, because 5 is the derivative of 5x. The one that people make mistakes on even more is if it's just e to the negative x. And when we take that derivative, we get e to the negative x, but then the derivative of negative x is negative 1. And usually we write that as negative e to the negative x. If my f of x was e x to the 5th, and I went to take that derivative, I've got an e to the something again. So the derivative of e to the something is e to the something times the derivative of whatever was in that exponent. And the derivative of x to the 5th is 5x to the 4th. Good times? What do we want more practice with today? Or is there another topic beyond product quotient chain rule that we wanted? Oh, so there's a question in the chat. So you take the derivative of the base and the exponent. Kind of. We take the derivative. So we take the derivative of like the thing that's on the outside times the derivative of the thing that's on the inside. It's a little bit harder to show an inside-outside function for e to the x. But yes, we're taking the derivative of the e to some stuff part and then times the derivative of the exponent. What do we want to see more practice with today? Messy derivatives. More practice with trig derivatives. More practice with finding equations of tangent lines. Cool, it's my choice. Sweet. So, I'm going to go with everybody's favorite, some more practice with trig. And I should have done this other commonplace where mistakes get made. But let's have a function that is secant of 3x. And let's, just for fun, find the equation of the line tangent to the curve at x equals pi over 4. Just for fun. Okay, so if I'm going to find the equation of a tangent line, I always need the same two things. I need a point and I need a slope. I gave us half of a point. So let's turn it into a whole point by plugging that x in to get a y value. So f of pi over 4, that's going to mean I'm looking for secant of 3 pi over 4. And I don't know about you, but I do not have my inverse trig function. Like I don't have my my secant, cosecant, cotangent facts memorized nearly as well as I've got my sine, cosine, tangent. So I'm going to choose to rewrite this as 1 over cosine of 3 pi over 4. If it's been a minute since you were doing some trig, we can think about unit circle. We can think about special triangles. My guess is that even if it's been a minute, as long as you memorized it previously, sine and cosine of pi over 4 tend to be the easier ones that people have memorized. You're probably thinking about that as 1 over square root of 2 or square root of 2 over 2, either one. So we're either looking at square root of 2 over 2 or 1 over square root of 2. Does anyone have a preference? You got it. Now, since we're looking at cosine of 3 pi over 4, I know that 3 pi over 4 is in the second quadrant. So cosine is going to be negative. So I'm going to have negative square root of 2 over 2. Or dividing by a fraction, the same as flipping and multiplying. So I would have negative 2 over the square root of 2. Which you could also just turn back into negative square root of 2. By multiplying the top and the bottom by the square root of 2. So now I've got my point, and now it's time to go figure out my slope. To find the slope, I've got to take a derivative. So I'm looking at this, f of x equals secant of 3x. I need a little bit of space, so I'm going to come down here. Well, that outermost function is secant. And the derivative of secant of something is secant of something, tangent of something. And the reason that I'm being careful about the something part is, and this one's important, calculus cannot change the angle inside of a trig function. Only trig identities can. So the angle inside of this secant right now is 3x. So the derivative of secant of something is secant of that thing times tangent of that thing. And a very, very, very common mistake would be to just write secant of x, tangent of x. But we can't change the argument or the angle that goes inside of a trig function just by doing calculus. Now I need one more piece here, which is the derivative of the inside, which is a 3. Question?
How apply it to like x cubed and yet to like put like secant like x squared times tangent of x squared.
Absolutely. So whatever's inside of the secant, we'd have to replicate that. So if it, I'll just, whatever, come up to the side over here. If this were secant of x cubed, then our derivative would look like secant of x cubed, tangent of x cubed, times the derivative of the inside, which would be a 3x squared.
So it also apply to like add like x plus 1, it'll be like secant of x plus 1.
Yep, absolutely. No matter how gross it gets inside of there, we've got to put it, the whole gross thing inside of the secant and the whole gross thing inside of the tangent. Yeah. Okay, so now I'm ready to evaluate this at pi over 4. So we're going to have secant of 3 pi over 4 times tangent of 3 pi over 4 times 3. And conveniently, we've just figured out what secant of 3 pi over 4 is. We know that's going to be negative square root of 2. Tangent of pi over 4 is 1 because it's the place where my sine and cosine values are equivalent. So tangent of pi over 4 is 1. And then again, we're in the second quadrant, which means tangent is negative. So I'd have negative square root of 2 times a negative 1 times 3. And I think that whole thing is going to work out to be a positive 3 square root of 2. So now I'm ready to actually write out our tangent line equation. Going back to our form, y minus y1 equals m times x minus x1. So I would have y minus negative square root of 2 is equal to 3 square root of 2 times x minus pi over 4. And I would walk away. So you could take the minus and minus and write that as a plus if you want. Yeah.
To simplify this to slope intersection.
So that really depends on how the question is asked. So certainly if you're doing a web work problem and it's prompting you to do this as y equals, then you've got to at least get this to y equals. Also, if the problem states that you need to put it in slope intercept, then you should. But if it just, like if it's a quiz and you're just writing answers and it just said to find the equation of the tangent line, this is usually sufficient. Yeah.